I'm Irina Kabakova, so I will be giving this last tutorial. So spectroscopy with frequency combs. Well, few of us have done spectroscopy, right? And few of us probably know that spectroscopy is actually a very old field. So Scott, in his lecture yesterday, went back to 1800s, to the times of Hertz, when he was talking about one cycle of oscillation. So I'm going to impress you. I will go to 1666. So spectroscopy exists for more than 3 centuries. And for more than 3 centuries, people were actually fine without combs. So they didn't need one, right? So my job is convince you by the end of this tutorial, why do we use 1 or 2 frequency combs to do spectroscopy. So we'll go and we talk about spectroscopy in general and what it means. And a few little history lessons. I hope you find them amusing or interesting, or perhaps if you, especially for professors here, if you find it boring, please read your emails. So don't worry about me too much. So then we talk about spectroscopy approaches to spectroscopy, and there are a few without frequency combs, and that's what people used for a very long time. And I'm not in any way going to cover all of them because there are a lot. I'm just going to cover 2 main approaches, then frequency using 1 frequency comb spectroscopy and then dual comb spectroscopy. All right, let's begin. So people kind of knew that light and colors are somehow connected because we all have rainbows, and rainbows were with us from the dawn of the world and civilization. And although people see those pretty rainbows, they didn't really connect rainbows, colors, and light spectrum until Isaac Newton came around, and that's second half of 17th century. And Newton did his famous prism dispersion experiments, where he took sunlight and he launched it into a glass prism, and then due to dispersion in the glass, meaning that different colors propagate with different speed, and also it means that they refract at slightly different angles, Newton was able to split white light into all these pretty colors and show that it is a rainbow, right? So I actually didn't know that the literal translation of spectroscopy comes from Latin spectrum and scopus, and it pretty much means ghost watching. So spectrum was translated back then as image, vision, or ghost, and then scopus is watching. Right, so we can all watch ghosts in our labs from now on. So the next stage in the sort of history of spectroscopy is related to William Herschel. And William Herschel was a German-English astrophysicist. And in around 1800s, what he thought about is to measure temperature of colors, different colors. And that's a rather fun experiment. Did you have Herschel type experiments in your undergraduate labs? Did anyone have Herschel experiments in undergraduate labs? I didn't. I wish I had, because they're kind of fun. So the idea is that you take a beam of light, and that was sunlight as well, and you split it using a prism, and you create a rainbow. And then Herschel was taking a thermometer and putting this thermometer at different colors. And then he was watching how the thermometer temperature rises, right? And it was rising from blue to green and then to red. And then he thought, what about the ambient temperature? And he put thermometers everywhere. And so happens that one of the thermometers was actually lying next to red color here. So after red color. And he was expecting the temperature to drop, but that's not what happened. Temperature continued to rise. So he was very puzzled about it and repeated it several times. And then in the end, he realized that there is some sort of light that we can't see. And he called it an infrared light. So, and that what pretty much led to discovery of infrared radiation. And now we know that what we see with our eyes is only here, but the electromagnetic spectrum of light is very, very broad, and what we see is only a little bit of it. And there is a lot of light in sun emission in infrared spectrum as well, and it's a very, very important spectrum. All right, so this is where Jean probably loves it, because this is a cornerstone of astrophysics, right? So next I want to touch on Fraunhofer discovery of the solar absorption features, and that would be the end of my history lesson, okay? I'm not going to bore you with that anymore. So Josef von Fraunhofer, he lived in Bavaria, and that was end of 18th century and early 19th century, and he was a very famous glass maker. So he was very good with making lenses, and he actually was the first person who discovered and invented the diffraction grating. So instead of using a prism, he made a diffraction grating, and he was able to disperse the spectrum of sunlight very, very well. And when he did it, he noticed that there were all these black things appearing in the spectrum, and that wasn't dead at all. So it was something which was actually real. And he measured it again and again, and he documented in his life 547 lines, right? So he was very thorough and documented it all, 547 lines. So little did he know that there are millions of lines, but you know, we are talking about 19th century, early 19th century. So the achievement of 547 lines is remarkable, and that's why these lines are called Fraunhofer lines. He actually, unfortunately, lived a very short life and died at the age of 39, because back then, if you're a glass maker, you pretty much breathe toxic gas all the time when you're making glass. So his life was very short, so not to be repeated. But the achievement is extraordinary because not only he was able to document those lines, all these lines in the spectrum, he also explained it. And he did it by following logic. So he thought, well, perhaps the lines there is light from the sun interacts with, I don't know, stratosphere, hemisphere of Earth. So all this gas, pollutions, and whatever pollution probably, I don't know, probably was less back then in 19th century, but nonetheless, so this is the absorption lines in the spectrum. And then he checked emission spectra from other stars, and he also noticed lines there, but those lines were not exactly at the same positions. So he made a very logical conclusion that it must be not the lines on Earth, atmosphere of Earth, it must be something different. And it has something to do with the star you're looking at. So actually these lines, they relate to the composition of the star. And the light that is emitted by the star gets absorbed in a way because it goes through the outer sphere of the star, which is usually gases, and composition is slightly different for different stars. So that's what the discovery was. So this, as we know now, is a spectrum of solar radiation, and what you can see here is black lines are these caves in the spectrum that pretty much the light is absorbed by some sort of gaseous substance, and we are not getting this light here on Earth. So to sum up, right? So spectroscopy works pretty much like this. We have to have some sort of light source. Then we have to pass it through the prism, we split it into colors, and we obtain a spectrum. So we split all the light into separate colors. So, and then if you put a sample, and in this case, it's a cloud of gas, then what happens is some of the colors will be absorbed by the gas, and that's depending on the gas composition, molecular composition, and we will have those dark lines, which we know now are called Fraunhofer lines. Make sense? Everyone is still awake? Good. Okay, so So how can we measure spectra practically? Well, we can use a broadband light source, and it could be coherent or incoherent, doesn't really matter. So it has a very broad spectrum, as long as the spectrum covers all of the spectral features that we need to measure. We pass it through the sample, and then we have to have a spectrum analyzer or spectrometer. So this is a tricky one. So it might be a little expensive, but what comes out of it would be a spectrum of our light source minus the absorption features. So whenever we have absorption feature, it will be a dip in the spectrum, that black line that Fraunhofer measured, right? So to realize that, and that existed for a very long time, we need to have a high resolution spectrometer. The spectrometer needs to be able to resolve these narrow absorption features, and we need a broadband light source. We'll talk about how to make a spectrometer later on and what requires for it. So let's just maybe look at a second solution, which is using a tunable light source, a very narrow line source that we can now apply instead of broadband light source. So it has high coherence, of course, because it's a SCW. And what we need to do is we need to it doesn't work? Yeah, it does work. So you need to tune it. So if you have a tuning mechanism, for example, by changing current or something like that, you can tune, you can shift it in spectrum. And in that case, you don't need a spectrum analyzer or spectrometer anymore. You just use a single pixel detector. Has to be a sensitive detector, but nonetheless, that proves to be a little bit cheaper scenario. Good. So spectrum analyzers. I mentioned that spectrum analyzers usually, if you want high resolution and broad range, they're quite expensive, right? And they're expensive because they have lots of bits, optical bits in each. And usually you would have a bunch of optics there, lenses, mirrors, and you also have an important component, diffraction grating, and that's the same diffraction grating that Fraunhofer discovered back then, but now fabricated in modern days. So it will have possibly thousands of lines, and these lines are those grooves. So it's aggregation of the surface, and grooves that, sorry, I skipped. So the grooves are periodically positioned, and the periodicity is very important. You choose your period of the grooves with regards to what wavelengths of the light source you have and what you want to obtain in the end. And if you want to construct a spectrometer which is very broadband, perhaps you need to use a few gratings, because each grating will be only effective for a specific region, right? For a specific spectral region. So you might end up with a construction like here, for example, where you have one grating for the visible light and second grating for the near-infrared light. So that's all good and good, right? But it may be a little bit problematic, because no matter how good is your grating, how many grooves you have in your grating, and how big is your pixel, how many pixels you have in your detector or in your camera, you'll still don't get to these resolutions. So any diffraction grating would have a resolution of perhaps half a gigahertz or so, maybe a few gigahertz. You would never get to a resolution of a kilohertz. Also, if you need to swap between the gratings, you might have some sort of piezos or some sort of motors to move things around. So the whole thing is not very fast as well. So it might be giving you one spectrum in a millisecond or a couple milliseconds or a second, depending on the model and how old it is. But it's not ultra fast for sure, right? So you see that there are a number of limitations here, quite complicated, not very high resolution, right? And also, it actually a good spectrum analyzer is about 50,000 Australian dollars, so it's not that cheap.